Can you see the screen?
Yes, sir.
So what is the title written? Can you read it?
State space of a quantum system.
Oh, very good. So now I am confident that I am presenting the same screen that I am trying to write. Okay. So the first question is with respect to the set of donkeys. Okay, so you have a function defined from set of 5 donkeys. I hope 5 is the number that I gave. To real. What does this mean? This means the domain of your function. So this is the function. Now the vector space is set of all functions, or whatever I defined, set of all functions. Now for a function, for f, the domain is set of 5 donkeys. So the domain is donkey 1, donkey 2, donkey 3, donkey 4, and donkey 5. And codomain, are where the function is going, is from the set of donkeys to. So what does that mean? So what is this V? V is basically, for each donkey I have to have one real number. So x1, x2, x3, x4, x5. For each donkey I assign a real number such that xi is a real number. Okay, so this is a vector space. You can verify all the axioms will be satisfied. This is a vector space. Now what is the dimension of this vector space? How many real numbers are required to write a arbitrary vector in this vector space? How many real numbers are required?
5.
One real number for each donkey. So one real number is required for each donkey, right? So essentially, this is what we call as set of 5 tuples. Okay, so 5 real numbers are called 5 tuples. Now, set of 5 tuples is a 5-dimensional vector space. So whatever number that I give, so set of n tuples is an n-dimensional vector space. Okay. So this is the vector space nature of this set of functions. So Mona Lisa, is that clear, or we have any adjunct question to this?
No, sir. So initially, when I was solving this problem, I was thinking about something else, like taking an element to prove the close identity. I was taking like something 0, and 0 means physically there is no donkey present, like that.
Yeah. So I mean, basically, donkey can take a value 0. Donkey itself will not be annihilated, but donkey can assume value 0. Okay, that is
So
a possibility.
Yeah, then sir, for the verification of the vector space, we will need to first prove that it is a group. So for the identity, we can take 0.
Yeah, yeah. Case. So your what is your identity? Identity is 0, 0, 0, 0, 0.
And sir, what about the inverse?
For every x1, x2, x3, x4, x5, you will have minus x1, minus x2, minus x3, minus.
But sir, physically it will mean nothing, I think.
What do you mean physically?
Physically, like when we are considering the identity case, we can say that there is no donkey present. But for inverse,
no, that's not what I'm saying. See, when I say 0, 0, 0, 0, 0, there is a map. in which every donkey can be mapped to 0. Now, I
Yes,
did
sir.
not tell you what this 0 is. Okay, let's say the amount of gold that every donkey has. I talk about that property. A donkey doesn't have any gold, so if I say the amount of gold that every donkey has is 0, 0, 0, 0. See, this is only our interpretation, right? So what we have to see is whether a given definition will allow for such an element or not. That's all that we have to worry about. Now, we should not give more emphasis on donkey than this, because so what is 0? 0, you are mapping a donkey to 0 doesn't mean that donkey itself is 0. Correct? Suppose if you are getting in some subject 0 marks, that means you are not there. It's not like that, no. So the amount of marks that you are getting in a subject, it can be 0, but you are not 0. So that is what we are saying. You can say you map some property of the donkey, and now consider set of all possible properties of these donkeys. Okay, even if you are not able to define a property, it doesn't matter. But this map will allow for 5 real numbers to be grouped. Correct? So in that sense, it is a vector space.
Yes, sir.
Excuse me,
I
sir.
got it.
Yeah.
So this question I understood like we are assigning a number for a donkey, like donkey first, like let be 5 donkey A B C D E, and I'm assigning every donkey A 1 B 2 and C 3 D 4 and E 5. And
Okay.
when I in inverse, I thought it like, okay, if I'm calling donkey number 4, so I will be associating it with donkey. So is this notion of inverse correct?
Your voice was not clear. It was in between breaking, so I could not hear it completely.
I
About the
will try.
inverse especially.
Yeah, like what I was saying, like I am assigning every donkey A, B, C, D, E to
Okay.
one number: A1, B2, C3, D4, and E5. And so when like I am mapping A to 1, B to 2, and C to 3, and D to 4, and E to 5. And when I am set to ask inverse, so it is like, okay, I'm mapping A to 1, B to 2, C to 3, D to 4.
Exactly at this point, your voice I could not hear. There is some symmetry where the voice goes off. Okay, so I could not hear you what you are saying. What I'm saying about the inverse is that is, suppose if I have x1, x2, x3, x4, x5. So this is one particular function. Okay, so I will call this as fa, for example. Then I will have a function fb, another function, where this mapping will be minus x1, minus x2, minus x3, minus x4, and minus x5. In as much as x1 to x5 are real numbers, minus x1 to minus x5 are also real numbers, such that this function f of a and f of b will be equal to 0. So this is what, so f of a is the additive inverse of fb, or vice versa. Fb is the additive inverse of fa. Okay.
Sir? Hello? Hello, sir, can you hear me?
Okay. So now let us maybe take up the other question. The second question is with respect to polarization.
Excuse me, sir.
Yeah.
Someone was asking a doubt.
Huh?
Someone else was asking a doubt. Actually, you didn't hear it.
I could not hear also. Has it been? Is it
Ritesh
typed?
was asking.
Hello, sir.
Yeah.
Hello, sir. Can you hear me, sir?
Now I can
Sir,
hear.
almost in all questions, I was able to find this inverse element, that inverse element and the whatever this initial properties. But can you give me example where that inverse element doesn't exist? Like whatever example you give, certain axioms were easily verifiable. For example, the real catch happened when there is a closure, or when we check for closure associativity only, the real problem arises. That's what decided whether it's a vector space or not in most of the cases. So my question is, can you give me a problem that the basic axiom like inverse will not even exist? Because I didn't find any example in my problem sheet at least where inverse doesn't exist.
Okay. Okay. So yeah, it's an interesting question, but answer probably is not readily available with me. But it is a good exercise. So let's say that we are interested in doing this exercise. That is, find an example. Find an example of a algebraic structure. Okay, of an algebraic structure V, vector addition, and a field such that it fails to be a vector space by violating only one of the axioms of the vector space.
Excuse me, sir, the answer can be a set of all real positive numbers, because its inverse will be a negative number, so that doesn't
Yes. So actually, that is already there in the list that I have given. Okay. So I guess this is the list that I have shared with you. So I think so if you look at D, 2 set of positive real numbers with vector addition is defined as x plus, okay, set of positive real numbers D1. Okay, so this
yes, sir.
particular
This is the what.
so this particular one, set of positive real numbers, this will not be a vector space. Not a vector space because inverse for each element does not exist. For example, x in R plus, but minus x is not in R. So this is an example for what Ritesh has asked. But now here I gave you another thing. If you define your vector addition in this way, okay, I want you to notice that whenever I say x plus y, it is x into y. And whenever I say scalar multiplication a into x, it is x power alpha. So if I modify that, the same set with this vector addition and scalar multiplication, it will become a vector space. Okay, so this is just to play around, and so this is
Hello, sir.
yes.
Sir, I tried that problem, but in my case, the distributive property is not working for that particular case. It is an abelian group I found.
Okay.
And also the multiplication is also satisfying, but the distributive property is not satisfying.
So distributive property is what? A times x plus y is equal to a times x plus a times y, right?
Yes, sir.
In general. So this is equal to a times xy, which is equal to xy to the power a. That is equal to x to the a into y to the a, which is same as a times x plus a times y. So there is no problem, right? So it satisfies.
Okay, so then I think I did it wrongly.
Yeah. So you have to understand this x to the a is a dot x, y to the a is a dot y, and x, this product is like plus. Okay, so that is how it is defined in this way. So there is no problem. Distributive property. So this is a vector space. Okay.
Sir,
And yeah.
is 0 involved in this positive real numbers? Otherwise, we can't find an identity for it.
Yeah. So when I say r plus, it is including 0.
Okay. Okay, sir.
Okay. So there are two things that I want to emphasize here. I'm sure you know it, but let me just emphasize in case if there is someone who does not know it. So whenever you are trying to that is to prove something, your argument has to be general. Okay. On the other hand, to disprove an example is sufficient. Okay, to disprove an example is sufficient. Okay, so this is something which you have to keep in mind. For example, let's say I have a set of all singular 2 by 2 matrices with real elements. Suppose you take this K. Okay. Now I want to show that it is not a vector space. Okay. So K, it is not a vector space. It's not a vector space. Now, how do that means I am not going to prove that it is a vector space. I'm going to disprove that it's a vector space. So now I have to take simply two singular matrices. Singular means what? Determinant is 0. So I can take two examples. Let's take 1 0 0 0. This is a singular matrix, and then I have 0 0 0 1. This is another singular matrix. Then addition of these two is this. Now this is singular. This is singular, and this is also singular, but this is non-singular. So that's all. One example I have shown you that I take two singular matrices, add, I get a non-singular matrix. That means this is not closed. So this is not closed, means it cannot be a vector space. It's not closed under vector addition. So like that, when you are trying to disprove, just an example is enough. But to prove, you cannot prove with any number of examples. Even if you give me infinite number of examples, I will not accept that as a proof. Okay, so proving has to be very general. Okay, so this point is very important when we are working.
So when proving, we can use this method of contradiction or this method of induction also.
Correct.
Really.
So either you use reductio absurdum, that means you assume something and then show that it is contradictory, or you use mathematical induction.
Sir, and one more thing, sir. In the last problem, I didn't understand how that x power a, y power a got added up. Like the final step. How did it become a dot x plus a dot y? Like I didn't see this property anywhere.
No, that is given. No, a dot x is equal to x power a. That means x power a can be written as a dot x. No,
that is fine, sir. But how the plus came in the middle?
Because x into y is x plus y.
Oh, okay, acha.
So x power a into y power a is x power a plus y power a.
Okay,
That is
I didn't see that. Okay. Sorry, sir.
Okay, so this exercise is nevertheless very interesting. I mean, if you can find examples, this set of examples, whatever A to Z I have written here, also is not with this kind of an exercise in mind, but it is a useful exercise to think of finding examples where each one of it is violated. So those of you who are curious can put in some thought and try to come up with examples where we can find examples where each one of this is violated, but others are satisfied. That's what it means. Okay, so now let's come to polarization states. So normally what do we say? We say that a polarization state means, so you can have, so normally you say that you have plane polarization, plane or linear polarization. Okay, in which case you can write down your electric field as electric field along x direction. Okay, so let's say Ex along x direction and Ey along. These are fields, that means they will depend on x, y, z. So Ex and Ey along two different directions. So assuming that this k direction is the propagation direction. So you can represent a polarization state as a column vector. Okay, so with Ex and Ey, and these are two amplitudes of the electric field. Now you can talk about, suppose you can have a situation where Ex is there but Ey is 0. Then you call that as X polarization. And Ex is 0 and Ey is non-zero, then you call it as Y polarization. Or you can say, you can abstractly write it in the following fashion. So let us say I have a horizontal polarization, which I will denote it like this. So this is horizontal polarization. And we are going to represent this as 1, 0. Similarly, I can talk about a vertical polarization. This is like X polarization. Okay, so we denote it as vertical polarization. And that is denoted with 0 and 1. Now I can have a diagonal polarization, which I will call it as D, where the axis is rotated around 45 degrees. So that is what we got, the normalization 1 by root 2 times 1, 1, or an anti-diagonal polarization, that means 135 degrees, which is 1 by root 2 times 1 minus 1, and so on. Now, the interesting aspect is that these are both the components are real numbers, but then suppose you want circular polarization. Okay, so circular polarization, there should be a pi by 2 circular polarization requires a phase shift between x and y components. So, for example, left circularly polarized light can be written as 1 by root 2 into 1 minus I. Okay. Our right circularly polarization can be written as 1 by root 2 times 1 I. So, you can see that in general, okay, a general polarization state can be written as, suppose I call that as some alpha, will be equal to C1 C2, such that this is normalized. C1 square plus C2 square is equal to 1, and the C1 comma C2 are complex numbers. So now if I define a vector space V, which is equal to C1 C2, such that C1 comma C2 belongs to complex numbers, then what this is a vector space. Okay, this is a definitely vector space, because 0 0 is the identity, and C1 C2 minus C1 minus C2 will be its inverse. Everything is there. So this is basically a two-dimensional vector space. Dimension is equal to 2, and V is defined over a field of complex numbers. Okay, so set of polarization states are basically complex number. It's basically, so we call this simply seat. Just like R2, we call this as seat. So C2 is the vector space of the state of polarizations. Okay, so a general polarization state, which are generally called elliptical polarizations. The general elliptical polarization state is simply two complex numbers, a vector of two complex numbers normalized to 1. Okay, so that is the state with respect to polarization. Okay, so yeah. So any other question?
So generally in problem sheet, if you don't define anything, for example, if you say set of real numbers, that means we have to take it as plus only, no sir. We have to look for the additive inverse, isn't it?
Yeah, vector space by definition, it's only vector addition that requires, I mean, a set of vectors with vector addition has to be an abelian group. So I have to look for only addition. If I want some other operation, then I should define. Otherwise, it is addition. Okay. So now let us try to proceed further. So there are certain examples in the vector space which I have given, but maybe we can have some discussion on that. So first, let us now look at the. Okay, there was another question. I think so there were closure of two straight lines. So first, how do we define a straight line? So straight line is defined as, so if I have, so this is x and this is y. Let's say I have an arbitrary straight line like this. This straight line is defined as y is equal to mx plus c. So what does that mean? That means this x is a variable. This is a variable, and minus infinity less than x less than infinity. That means it will take all the values. Now by fixing m and c, I get the straight line. I am getting the straight line means I am using up all the values of x. Okay. So what defines the straight line? This m and c. These two define the straight line. Define the line. So this x should be used for all lines. That's what it means. Now suppose if I say that I have another line like this, okay, so this will be y is equal to some m prime x plus c prime, because what is the difference between this line and this line? X common. X is, all values of x has to be used to define the straight line. Now once that is true for all things, only thing that will change is the slope and intercept. So this is m prime and c prime will define this line, m and c will define this line. Now if I am adding these two lines, that means the addition of these two lines, so let us say this is line L, this is line L prime. Now L plus L prime, okay, has the equation. Now y and x don't change. Y is equal to m plus m prime into x. For that also whole x has to be used, plus c prime. Now m plus m prime is another value. It will be another real number. C plus c prime is another real number. And hence, this will be also a line. Okay, this will be another straight line. So when you consider set of all straight lines, it is closed. And what is the identity? What is the identity?
0 plus 0x.
So that is basically y equal to 0. So that is x-axis. So x-axis is the identity. Okay. Similarly, for every y equal to mx plus c, there will be y equal to minus mx minus c. And when you add these two, you will get this y equal to 0. Correct. So like that, inverse exists for each line. Okay. Now you ask a question, what is the basis? Okay, so the basis will be two lines. What are the two lines? Y is equal to 1 is one line, and y is equal to x is another line. So if you want to see how it, so you have one line which is y is equal to 1, this is y equal to 1, and then one line which is 45 degrees line, that is y equal to x. Now you multiply this with some constant, this with some constant, any arbitrary line can be up. So this is this is the algebra with respect to the straight lines. Okay, now we can ask a question.
So
Yeah.
One question.
Yeah.
So we have defined the straight line to be y equal to mx plus c. We can define it using x also, right?
Using what?
Using x. Sir.
You mean x equal to some
y minus y by m minus c.
Yeah, that is okay. This is a linear equation anyway.
Yes, but there the identity will be x equal to 0, not y equal to 0. So will that be forming a different vector space than this one? Because it will correspond to the same lines. but the identity will be changed. Just x equal to 0.
No, I think it will be simply restating this. Okay, the identity it is like inverse of this map, right?
Yes.
You have this and you have inverse of this map.
Yes, sir. The maps are changing, but the things that it represents are remaining the same. Just represent
Yeah,
it in a different way.
yeah, that's right. So, so if you want to generate, this, it is like it's like changing the independent variable, right? So
Yes.
then I think the changing of identity is okay.
Similarly, the
Some
basis will
identity should
also.
exist. Basis also will change. That's okay. It's only description is changing. That's all.
Yes. So it will remain the same vector space.
Yeah.
So the basis will be also the same, no, sir? Like it will be x is equal to y and x equal to 1.
Correct. That's what he
Oh,
is
that's
also
it,
saying.
right? It's like similar, same thing only. Like I'm like just in place of x, y will come. In place of that's it. That's the only change.
Yeah. Correct.
Yeah.
Okay. So now let's try to proceed further. So let's say that I am interested in finding out. So now let's consider set of all. So my vectors are V is set of all polynomials um, of a single real variable.
Sir,
We call it as x.
so there is some question in the chat box.
I don't have. Let me see. I set of all solutions or differential equations with initial conditions.
I think she's asking to solve the question, I guess.
Veda, what is the question? Veda?
Sir, it's the question number Y from the problems that you gave.
Oh, okay. Okay. So, okay, let's come back to that question. But before that, we'll just discuss this example. So, suppose you have set of all polynomials of single real variable x. So, set of all polynomials. That means the order of the polynomial can be anything. So that means, or maybe polynomials uh, of degree less than n, let's say. So then you are going to have your V as defined as a set A0 plus A1x plus A2x square, etc. less than n. So it has to be an minus 1 x to the power n minus 1, such that x is a real number and a0, a1, etc., an minus 1, they are all real numbers. Okay, so these are set of polynomials. Now remember, each one of this, okay, that is for a fixed a0 to an minus 1, an minus 1. The polynomial is a curve. Okay, so let me call this curve as some p of x. P of x is equal to this. Is a curve p of x. Now you choose a different coefficients, you get a different curve. So set of all polynomials will be all possible curves up to this order n minus 1. Now just like, so in terms of this, what is the set of all straight lines? Set of all straight lines is set of all polynomials of degree less than 2, either constant or linear in x. So it will be such that. So the above example is just a sub case of this one. Okay, so you can have this situation, and this is like, see now this 1x x square, these are like donkeys. Okay, one is one donkey, x is one donkey, x square is like another donkey. So for each donkey you have to associate one real number, that is a0, a1, etc. So I could have written this vector space as a0, a1, etc., an minus 1, such that a0, a1, etc., an minus 1 are real numbers, because that full x is there for all these polynomials. So the set of all polynomials of degree less than n is basically this n tuple, correct? So this is n tuple. So this becomes a vector space, okay, and the dimension of this vector space is equal to n. Okay, this is an n-dimensional vector space. Now I can make a generalization to this. Now suppose if we consider, now I define V to be set of all polynomials. Set of all polynomials. Set of all polynomials of any order, of any degree for that matter. Set of all polynomials. That means what? You are going to define your V as a0 plus a1x plus, it goes on and on and on and on. There is no upper limit, such that ai is, they are all in real numbers for all I equal to 1 to infinity. Okay.
Sir, 1 moment, sir.
Yes.
In the previous question, if you define the previous question, I mean that less than n.
Yeah.
If you invoke a condition such that x of 0 equal to 0 and x of 1 equal to 1, will it be a vector space, sir?
What? X of 0 is what?
Like in the previous case, the same question. If you tell that x of 0.
What do you mean by x of 0? X can be 0 or x can be 1.
Like I'm telling a function, sir. Like I'm telling a function such that x is equal to x of 0 is x of y, p of x, that is equal to 0, or p of p of 1 equal to 1.
Okay, I know what you're asking. We'll come to that.
Yes.
So what I want to drive home here, the point is that if you consider a set of all polynomials, then what will be the dimension of this vector space? How many real numbers are required to define a polynomial? You require infinitely many of them, because the degree is, it can be anything. So the dimension of this vector space is infinity. Okay. Now this infinity, but remember that each of this polynomial, that is each element of V, a polynomial, which I will call it as some P of x, is a curve. on a plane. Okay, I will be able to draw, I can always draw, I take some x and y, and then this will be some kind of a curve like this. This will be your y equal to p of x. Correct? I can draw this. Now when I consider set of all possible curves, when I say set of all possible polynomials, that means there are different curves on the plane like this. Now that set will form an infinite dimensional vector space. It is in this sense that we have to deal with infinite dimensional vector spaces in quantum mechanics, even though we are talking about a particle in a box, which is even a one-dimensional problem, or a hydrogen atom, which is electron in a hydrogen atom, which is a three-dimensional problem. But the state space, it will deal with possible functions, set of all functions that you can define on a plane or in a space, and they will be forming an infinite dimensional vector space. Okay, so I wanted you to notice that even if I take a plane, when I consider set of all polynomials, I have infinite dimensional vector space. Now let us try to look at another example. This example is, so now I consider the vector space V is set of all functions f of x such that x is between 0, 1. Okay, x belongs to 0, 1. That means I am having 0 here, 1 here. This is my x, and I can have some function like this. So this is my f of x, and I can have another function like this. Okay, so this may be my g of x. Like this, I consider set of all functions, and then I consider set of all functions, and this will become a vector space. What is the identity? Identity is equal to f of x is equal to 0 for all x. That means that function will be simply like this, f of x equal to 0.
Sir, will it be the same criteria for function space also, sir? We call so there's something called as function space.
This is function space. So vector space of functions is called a function space. Okay, so now so basically this function, just like what we have defined earlier, so this function, so this f of x is defined from 0, 1, the interval 0, 1, to real numbers, or you can say it can be defined to complex numbers, it doesn't matter. But this is how many so the question that we are now trying to ask is, what is the dimension of this vector space? What is the dimension of this vector space? Now, to define an element, of V, namely f of x, how many real numbers are required? How many real numbers are needed? This is the question that we have been asking, right? To determine the dimension. Now, how many real numbers are required?
Infinite.
You require infinitely many real numbers, because between 0 and 1, every value of x you require a real number. Now, this infinity is different from the infinity that we have written here, because this infinity is a countable infinity. That means you require 1, 2, 3, 4 up to infinity. This is a countable infinity. Whereas here we have the dimension of V is an uncountable infinity. This is an infinity, but this infinity is uncountable because between any two there are infinitely many. Suppose I have x equal to 0.1 and 0.11, and between these two I require infinitely many real numbers. So this infinity is different from that infinity. This is much bigger infinity than that infinity. So we call this as countable, or sometimes people are also called denumerable. That means you can enumerate. This is a denumerable infinity or countable infinity. This is a non-denumerable or uncountable infinity. Okay, so now let's look at the question that so now let's say that you take. So once we understand this, then we try to modify this a little bit. Suppose now you consider V as set of all functions f of x, which goes from, let's say, 0, 1 to real numbers, okay, such that f of 0 is equal to 0 and f of 1 is equal to 0. Okay, now these conditions are called boundary conditions. Boundary conditions. Okay, now you can ask a question. If you are having a boundary condition like this, so not all functions of the above vector space will become members of this vector space, right? For example, if you have a function, okay, so suppose let's say this is your x and this is 0 and this is 1. Let's say you have a function like this. Okay, now this is not so this is not in V, because f of 1 is not equal to 0 here. So this is not in V. Okay, so but you can have a function like this. Okay, so this is in V. Now if you consider, so that means if you look at the previous example, okay, if this so let us call this as okay, so let us call this one as V tilde. Okay, so this is not in V tilde and this is in V tilde. Okay, but notice that V tilde is a subset of V. V tilde is a subset of V. Okay, it's a subset of V. Now, whether V tilde also forms a vector space, that is something which we can verify. Okay, and you can show that V tilde also forms a vector space. Okay, so V tilde is a vector space. Okay, now let us look at another example. So we will call this as, let's say, V prime. V prime is equal to set of functions from 0, 1 to R such that f of 0 is equal to 0 and f of 1 is equal to 1, let's say. I've changed the boundary condition. Same function, but I've changed the boundary condition. Okay, so note that V prime is also a subset of V. V prime is also a subset of V. But is V prime a vector space? Is V prime a vector space? Okay, if you ask that question, The answer is no. Can you tell me why it is no? It's not a vector space. The answer is no. Why it is not a vector space? What axiom will it satisfy? Will it violate?
Closure.
Closure is not satisfied because you take any two functions in this, then f of 1 of the sum will be 1 plus 1 2, but it has to be 1. Okay, so closure is violated. And more importantly, there is no identity. No identity because f of x equal to 0 is not in this V prime. Because if f of x equal to 0 for all x, that means f of 1 is also 0. But that is not a part of this set at all. So there is no identity. As a result, this is not a vector space. Now, let us come to this question of so let us say that we have some let's say that we have some differential equation. Okay, so let's say we have some differential equation. Let's say this is some differential operator and it is operating on y of x is equal to 0. So let's say this is a differential equation. Okay, and to be specific, let us call this L a second order differential operator. Okay, so now what happens? We have two solutions: a second order differential equation, second order ordinary differential equation has two solutions, has two linearly independent solutions. We'll call them as some y1 of x and y2 of x. Okay. So what is the general solution? General solution y of x can be written as some c1 times y1 of x plus some c2 times y2 of x. Now this is a family of, okay, so basically this for c1 c2 fixed, we get a solution, and that is c1 and c2 can be fixed by using initial condition. But if you don't fix them, okay, so for arbitrary c1 and c2, this y of x is equal to c1 times y1 of x plus c2 times y2 of x is a family of solutions, family or a set of solutions. Okay, now to find a general solution in this set, how many scalars do we need? We need two, namely P1, P2. Therefore, the set of all solutions of a given second order ordinary differential equation is a vector space of dimension dimension 2. Okay. Now, I also want to make a remark here. Okay, so suppose we have a partial differential equation. Okay, so let's say we have a boundary value problem. So what is a boundary value problem? Essentially a partial differential equation like Poisson equation or diffusion equation Schrodinger equation okay, we have a partial differential equation with a given boundary condition. Now, set of all solutions of a partial differential equation. Okay, set of all solutions of a partial differential equation is like a vector space I have defined like V here. Now, with the boundary conditions specified, it is like V tilde and V prime. Now, sometimes the boundary conditions are such that the solution subjected to that boundary condition will become a vector space. Or sometimes the boundary conditions are such that the solutions with a given boundary conditions do not become a vector space. Now, whenever there is a vector space structure for the solution, set of all solutions, then mathematically handling such equation and such boundary value problem will always be easier. So some problems we can solve, some problems we cannot solve. So whenever there is a vector space structure for the underlying solutions, then dealing with such problem mathematically becomes very easy. So it is in that sense that so vector space structure for a set of solutions of a given partial differential equation with specified boundary condition. simplifies. Otherwise, we may not be able to solve it easily. One has to go to computer and solve that problem numerically. Okay, so this is a remark associated with this one. Okay, so maybe I will just leave this here with these examples and try to move to next concept that I have to introduce, namely, so let us try to look at most familiar vector space. So the most familiar vector space is three-dimensional Euclidean space, okay, which we will call it as R3. Okay, so this is basically three-dimensional Euclidean space. Okay, which we define it in the following fashion: R3 is equal to x, y, z, such that x, y, z are real numbers. Are real numbers. Now, a general vector. Okay, so a vector can be represented abstractly as a ket vector P, and this V can be written as a column vector consisting of V1, V2, V3, and these are basically components. And you can write a vector in terms of its components once you choose a basis, a chosen basis. Now, typically, we will write this I as a unit vector along x-axis with a column vector like this, and j as a column vector like this, and k as a column vector like this. Okay, so this becomes one of the bases. As we said, basis is not unique, so this is a basis. Okay, so that you can write down this arbitrary vector V can be written as V1 times I plus V2 times J plus V3 times K. Now, the column structure that I have written for this ijk, it will tell you that this will be equal to V1, V2, V3. So, this is related to V1, V2. Now, let us define something called okay, so first let us try to understand this carefully. Suppose I have a function. How do I define a function? A function f of x, a function f of x is always defined like this. That is, I have some kind of a block box. Okay, I will call that as f. Now, there is an input. X is going to be the input, and f of x is going to be the output. So now if you see, this input is a scalar, a real number or a complex number, and f of x is also a scalar. Okay, this is also a scalar. It can be real number, it can be a complex number, but it's a scalar. This is how function is. No, a scalar will go in, a scalar will come out. Suppose if your f of x is let's say x square plus 2. Okay, so suppose let's say your function is such that it is x square plus 2. Then suppose if you are sending in 2, then that will what will come out is 2 square 4 plus 2 6. So 2 is a number, 6 is a number. So whatever number you send in, one number will come out. So this is how a function is. Okay. Now we will define something called a functional. Okay. We will define something called a functional. Now what this functional does is that you have what goes inside is a vector. A vector goes inside and then a scalar comes out. A vector goes in and a scalar comes out. Okay. Now what does that mean? That means, so the input is, so here input is a scalar, output is a scalar. Here input is a vector and output is a vector. Okay. Now we have
Output is scalar.
Output is a scalar. Yeah, input is a vector and output is a scalar. So this is what we call a functional. Okay. Now, so let me now define. Suppose I have a vector v. Okay, so let's say I have a vector v. Now that goes inside. Okay. Now this particular functional, okay, I am going to represent this functional with a symbol like this. Okay, so I will represent this functional with a symbol like u. Okay, so what is the scalar that comes out? U v. So this is a scalar. U v is a scalar. So now what you can see is that for every vector, v, we can define a functional denoted by a bra p such that v is a linear functional from set of vectors, that is the vector space, to the set of real numbers R. Okay, so this is a linear functional from R3 to R. That means you start, your input is a vector and output is a scalar. Okay, so that means I take this v and then u is in R for all u in R. Okay, Now, this V can be represented in the following fashion. If we know the components V1, V2, V3. This is a row vector associated with the components, that is in a chosen basis. In a chosen basis. Okay. Now, if the field is complex, that means if the scalars, are complex numbers, then we have to write this V as V1 star, V2 star, comma V3 star, where the star denotes complex conjugation. Okay, star denotes complex conjugation operation. Okay, such that when I take V and some U, I will have V1 star, V2 star, and V3 star, and U1, U2, U3. This will be a scalar. V1 star U1 plus V2 star U2 plus V3 star. So this is a complex number. Is a complex. Okay. Now one can talk about. So let us say that. So let's write this in a general language. So in general, let V be a vector space. Let V be a vector space. And let V in V be a vector. Okay. Then U are vector. Then this bra V is a linear functional from V to set of complex numbers in general. Okay. Now consider the set of all such linear functionals. Call it some V star. Call it V star. Okay. We can show that V star is a vector space. V star is a vector space. Now, V star is called the dual. V star is called the dual of V. V star is called the dual of V, or sometimes people call dual space of V. Okay. Now what happens? You have a vector space. You can talk about its dual. Then you can, so for any V in V and a linear functional U in V star, we can define U V as an inner product. An inner product, because remember, this bra U is a linear functional associated with some ket U in V. So that is what we wrote earlier. So inner product of two vectors U, V in V. But remember, to define an inner product, I must take this U and consider its linear functional bra U, and then multiply bra U with V. Then only I will get a scalar. Okay. So inner product is basically, so this gives a scalar. So UV is a scalar. Okay. Now you can see some properties of this inner product structure. Okay, so notice that the structure has the following properties. A, your UV is equal to VU. This is a scalar, this is a scalar, but then it will be related by its complex conjugation. UV is equal to VU star. This is a complex number, and what will this be? This will be whatever is the relation, you take a complex conjugate of that, that will be equal to this. Okay. Secondly, suppose I have U into some kind of a alpha into V. Alpha is some scalar. Okay. So this is same as alpha times U into V. Okay. This is linear. That means I can pull alpha out. Okay. Similarly, you can see, suppose if I put alpha here, that is alpha U times V, then what comes out is alpha star, because with the bra vector you always take rho and then the star of that. Okay, so this is called alpha star into UV. If alpha is to the ket, then it will come out as alpha. If alpha is to the bra, then it will come out as alpha star. Okay, so these properties can be easily seen for something called an inner product of this. Now, in general, if you have a set of functions, okay, so more importantly, this inner product, so the inner product induces a norm to each vector. That is, for a given vector v in V, so the norm of vector V denoted by, we will denote it by this symbol, right? VV. So that is equal to, take the inner product of the vector with itself and then take the square root of that. So that is going to give you the norm. Okay, and note that VV is a positive real number. V can be complex, but VV is always a positive real number. Okay, in other words, if you imagine that your V has these components like this, V1, let's say you have n-dimensional space, V1 to Vn, then your V will be equal to V1 star to Vn star in a chosen basis. Then your VV is basically sum over I is equal to 1 to n Vi star into Vi, which is basically equal to sum over I is equal to 1 to n Vi modulus the square. Everything is real and positive. This is 0 only if, so this is another property, that V is greater than or equal to 0 and VV is equal to 0 if and only if this V itself is a 0 vector. That means it's a null vector. Okay, every component of V is 0. Only then the norm of that vector will be equal to 0. Otherwise, it is always positive. Okay, so this is, so now if you have, so we have a vector space. Okay, a vector space V in which an inner product structure exists. Okay, so we call it an inner product space. So when we say I have an inner product space, that means I can define an inner product. That means that vector space is there. Then I can define a dual of the vector space. Then I take one element from the vector space and one element from the dual, and then I can define a scalar. So all this, if we can do, then we say that we have a slightly a better structure or a more structure to the vector space. It's called the inner product space. So the familiar inner product space for us in vectors is the vector dot product. So dot product is the inner product for Euclidean space, three-dimensional Euclidean space that we are familiar. So in R3, the inner product is the dot product. Okay, so this you can probably easily realize that the dot product is basically referred to as an inner product here. Okay, so Now we would like to generally ask a question that we have understood vector space in a very general sense. See, we said we initially started with a vector, and then after that we generalized, okay, vector need not be always a vector that we think of. Vector can be a function, vector can be a polynomial, vector can be a straight line, vector can be a matrix, and so on and so forth. Okay. So if vector can be a very general element like that, then we must be able to also define this inner product for general elements, right? So now we ask a question that how do we define this inner product? Okay, so the question is how to generalize the notion of inner product to a vector space of functions. A vector space of functions. Okay, so that will be our next question. Now this is very important because most of the times, as we have seen, that our quantum states, our quantum system has to be represented by some function. So when we say set of all states, we have to consider set of all functions. Like we said, set of all functions from 0 to 1, 0, 1 to r. So like that, we have to consider some set of all functions. So when we say, okay, we have shown that set of all functions will become a vector space. Now it is important to define an inner product for these vector spaces. Okay. So suppose if I have two functions, how do I define an inner product? So let us consider the set of all functions like this. So consider V is equal to set of all functions f of x. Let's say x is going from 0, 1 to real numbers. Okay, so let's not worry about any boundary conditions. Let's say we take this set of functions. This is a vector space. Okay, so we have argued that this is a vector space. Now we have also said that the dimension of this vector space is actually uncountable infinity. Infinity, that to uncountable infinity. Okay, now let us try to understand this carefully. Suppose, let us say that let us consider. So I am actually presenting an argument to generalize this. Okay, so let us say that let's say this is 0 and this is 1. Now let me say that for some reason I do not know the function completely. Okay, let's say that this is basically a solution of some differential equation and I cannot solve it analytically, but I have some kind of a numerical solution. That means I know this value of f only at some discrete points. Okay, so let's say I know the value of x, so value of f at this point, and at this point, at this point, at this point, this point. So I have the value of x at these discrete points. Okay, so this is one function for me. Okay, now I can also say that I know all other functions also only at these points. So let's say this is another function. Okay, so this so just for the guidance to the eye. So let me draw this. So this is some kind of a red function, and then I am guessing this would have been the function, but with the available knowledge of only these points, I cannot say this is the function, but this is some kind of a guess. Because between these 2 points, this function might have gone to infinity and come back. I have no idea. If I have only these discrete points, at points where I have no information about the function, I will not know what the value of the function is. So the solid line that I am drawing is just my guess. Okay, so let us call this black fellow as some f and this red fellow as some g. Okay, so at some resolution, we have, I'm going to call this as f, which can be written as f1, f2, etc., some fn. There are only n values at which, and I will define this g as another function, which is also g1, g2, etc., only gn, where we can say that f of x1 is equal to f1, or f of xi is equal to f of x. So that is how I have the notation. Now at this resolution, suppose if I want to ask what is the, so this is an n-dimensional vector space. So you define your vectors, okay, set of all functions, at this resolution, okay, which I will call this as some v tilde. Okay, so what is the dimension of v tilde? Dimension of v tilde is n, because this is n tuple. So at this resolution, we have a dimension of this to be n. Now you ask a question, what is this g and f? That is the inner product between these two, which is well known, and we know that that is equal to sum over some I is equal to 1 to n gi star into fi. This is a scalar, a complex number. In particular, the inner product of f with itself is equal to I is equal to 1 to n mod fi square. Okay, so this is the description at this resolution. At this resolution, we have this description. Now let us say that we can improve the resolution. Let's say that I get more money and I buy a better computer, and I will get the information at those in between values also where I did not have information earlier. Okay, so as we improve the resolution, f, g, etc. can be determined at more values of x. Okay, in the limit of improving my resolution to the extent that I get the entire function, that means the whole function. Okay, then what happens? How many values of n will be there? It will be infinitely many values of n will be there. Okay, so that means the way I define my inner product is equal to, so I am going to have I is equal to 1, 2. I have to have n to be infinity and fi the square. Now look at this one. Fi mod square is greater than 0 for all I. That means this quantity is the sum of infinite positive constants. Sum of infinite positive constants, this goes to infinity. That means the way we define it, the inner product, the norm of every vector. So this implies what? This implies the norm of every element of V is infinite. This makes no sense. Okay, so we should not have such a definition of inner product which gives you norm of every element to be infinite. So this requires a modification. Now how do we modify this? We say that the difference between these values of x, so we call this difference as some delta. Now notice that as n goes to infinity, delta goes to 0, because more and more x values you know, then the resolution, basically delta is like the resolution will be finer and finer, resolution will be there, so delta goes to 0. So what we can do is that we define this f as sum over I is equal to 1 to n modulus of fi square, and since this goes to infinity as n tends to 0, you multiply this with, so as you can see that this goes to infinity and this goes to 0, so that the product will remain finite. So that is the idea. And if you do this and evaluate this one in the limit n tending to infinity and delta tending to 0, this can be written as integral from 0 to 1 f of x modulus square into dx. So this is going to be a new definition of the inner product for the functional spaces, for the vector space of functions, where you can now define an inner product. Okay, so the inner product of two functions, f of x comma g of x in this vector space V is given by, so let me use this notation for the time being, f of x comma g of x, okay, I use a bracket notation, is equal to integral from 0 to 1 f star of x into g of x dx. So this is a general inner product definition generalization to the function spaces. Okay, so this argument that I have used here is essentially another heuristic argument, and if you want to read about it, there is a book by R. Shankar on quantum mechanics. So R. Shankar's book, in the first chapter of R. Shankar's book, this argument is presented, how you generalize this definition of inner product to set of functions. So you can always take a look at that argument. Okay, so I will stop here, and if you have some questions.
Sir, couple of doubts, sir.
Yeah.
One is this: how did you get the limits of the integral, sir? Like you defined it in the first itself,
No,
the
I have
function.
chosen this vector space.
Yeah, that is one thing. And second one, that isn't it greater than or equal to zero, sir? The norm, why it's greater than zero?
Uh, yeah, so the essential point is that it is equal to 0 only for the 0 vector. For every other vector, it is non-zero.
So we can write greater than or equal to zero, sir. There, f star f,
No,
fi square.
when I take a f, I will not take 0 vector. No, I will always take a non-zero vector. The moment I take non-zero vector, it is not going to be
You're giving zero.
0. No.
Then that's fine, sir. Why you are limiting it? You're not doing zero, sir. Any reason for not doing zero vector?
No, the norm of 0 vector is always 0. So that
Zero.
is a trivial case.
You are like neglecting the trivial case.
Yeah.
Okay, sir. Thank you, sir.
Excuse me, sir.
Yeah.
Sir, here we
Yeah.
are
Go ahead.
defining limit 0 to, here we are defining the integral limit from 0 to 1 because we had taken a function 0 to 1. So sir, I want to ask that here, is it anything to do with probability, like why we are taking only from 0 to 1?
No. I'm just taking that as an example. You could have taken from a set of functions from R to R also. Okay, this is just an example. Nothing to do with the probability.
Okay, sir, if we are decaying, then we can change, if we are changing our function, then we can change our integral limits as such.
Exactly. That's
Okay, sir,
right.
thank you, sir.
Yes, sir. Sir, I have a doubt. Here, do we
Go
are
ahead.
consider
Yeah.
here do we are considering a curve consists of infinite number of discrete points where every point has a basis in that coordinate system.
Hmm.
As we connect these points, we will get the curve.
Hmm. Are you asking me whether we will get the curve?
Yes, sir. If we connect this infinite number of points with basis, every point has basis.
Yeah, you will get the function. If you know the function at all points, then that is the curve. So here, even though I know only n points, I am trying to just connect them. But this is probably not the curve because I don't know between these 2 points what is the value of the function.
Yes, sir.
So this is just a guide to the eye. But actual value of the function, if you want to know, you should know the value of the function at all points, at all the infinitely many points.
Yes, sir. Sir, another doubt. In the properties of scalar product, do we need transpose with complex conjugate?
Mm-hmm.
In the first.
Yeah, so I mean UV is basically equal to VU star. Is that what you're asking?
Yes, sir.
Yeah, so if you interchange U and V, then you will get a complex conjugate.
Sir, do we need transpose also as bra is a column vector?
Oh, transpose.
Yes, sir.
No. See, the resulting the bra is anyway transpose. No, by definition, bra vector is a transpose vector, right?
Yes, sir.
Bra is anyway transposed. So when you multiply a bra with a ket, you get a complex number, and that complex number has to be just taken a conjugate. Okay, so there is no transpose required here. Transpose is there in the definition of a bra vector.
Yes, sir. In the interactions of bra and ket in the first property of the scalar product.
Yeah. That is sufficient. So what I'm trying to say is that I think we are talking about this property here. That is,
Yes,
so as you can see here, that so we could have written like this. Suppose I have U, okay, and then I want to write this bra, then you must write this as U transpose and then conjugate. Okay, but I'm already writing bra here, right? So then I don't have to take
Yes, sir.
transpose, only the conjugate part I have to take.
Okay, sir. Thank you.
Excuse me, sir. So I
Yeah.
have one more question or doubt. So, like here in the whole formalism of vector space, the linearity is taken into greater account. So can we say that the non-linear vector space doesn't exist, or there is some other formalism for it?
So basically, vector space is by definition linear. There is no nonlinear vector space.
So that's because we have developed our formalism by taking account in linearity. So why we can't develop our formalism by taking account non-linear regions and space?
See, if you have nonlinearity, then there are mathematical ways of dealing with that one. But so they are called manifolds and things like that. But with this kind of a structure, a vector space structure will not be there if you don't have linearity.
Okay, sir.